injections. The third one, the light blue one color, is combination of the two above. So it is the focus liner with the bottom taper. Because of addition of the wool and the taper, it is suitable for the trace level analytes, for dirty samples, as well as for wide boiling point range of compounds due to the presence of the wool. The fourth one, orange one, is connectite liner, and as you can see, the shape at the bottom, it has a narrow neck. And this is this design of the liner is suitable for direct injections, for active compounds and trace level analytes. The purple one is just the most simple straight through liner. It can be suitable for split as well as the splitless injections, for concentrated samples, for gaseous samples, and with the wool present, it will be suitable also for dirty samples. And the last one at the bottom is double taper liner. So it means it has a taper at the bottom as well as the top. So the contact of the sample will be with the sides of the injection port will be minimal in this design. So this type of the liner will be recommended mostly for active compounds, for trace level analytes. I hope this information will make your choice of the liner easier. If you still have a problem with that, we do have material available on our website outlining all of those informations, as well as some examples to which particular applications different geometries can be used or shall be used. So going away from the geometries of the liner, the liners are going also through the deactivation process. So deactivation is making the surface of the glass of the liner not active, and we can observe that in our analysis when we are comparing the activity. But we've heard today the terms of split and splitless injections. So maybe I'm gonna mention shortly what's the difference between them. So the splitless injection is done when we are injecting our sample and we are not splitting, not discarding any part of our sample of our gas in our injection port. So all of everything is going down onto the column. And split injection, on the other hand, is when we are injecting our sample. It's vaporized in our injection port, but some part of our sample is discarded in our injection port through the split vent, and just part of our sample is going down onto our column to be analyzed. So that's the difference between split and splitless injection, and the split ratio will be different for depending on how much of the sample we want to go through the column and how much of the sample we would like to be discarded. So during those two types of injection, our sample is spending a different amount of time in our injection port. So in the splitless injection, this time is usually longer than in split due to the lower flow of the gas in splitless injection. And on the top chromatogram, we can observe that our compounds, due to long residence in the injection port, had degraded. So when you're comparing the top and the bottom chromatogram, you can see that at the top, the aniline peak is much smaller, much lower height, as well as you're not able to see at all 2,4-dinitrophenol peak, pentachlorophenol lower. We are not able to see enderine peak at the top, and this means that our compounds, which we would like to analyze, has been degraded, have reacted with the sides of our injection port or our liner. But on the other hand, in the split injection, where our sample was staying in our injection port for much shorter time, so like 3 seconds comparing to the above one for 1 minute, we can see all of the peaks which we would like to see, and heights and the peak with the peak areas suitable for us for analysis. So this is what we would like to see. So it's important to optimize our settings and choose what type of injection we would like to perform in our analysis. And talking about deactivation of the liners, here the industry standard test to check the quality of the liners is by measuring enderine and DDT breakdown. So in a good liner, we can see the nice high peak for enderine and DDT. In the bad liner, where we can see some activity, so our sample has reacted with the sides of the liner, where this glass was not deactivated, we can see the enderine peak is significantly lower. And as well, we can observe the breakdown products of enderine, such as enderine aldehyde and enderine ketone. The other compound taken into consideration and its breakdown products is DDT. So you can see higher peaks for DDE and DDD, so breakdown products of DDT in the liner, which is not as inert as it should be. And you may be familiar with that. There is few kinds of deactivation present on the market, and depending on your analytes, different might be more or less suitable. But in a short rule, if you're analyzing very active compounds, the more inert liner should be. So talking about liners, they don't last forever, unfortunately. So they can also become dirty in our injection port, either through our samples, the nature of our samples, or can gather the buildup of the septa material. Here on the photos, you've got example of how the dirty liner can be looking like. So all the black rings at the top of the wall is just the dirt from our sample, and this is signal for us that the liner have to be changed. And here we've got 2 chromatograms comparing the clean deactivated focus liner and old dirty liner, and you can see that the old dirty liner, you've got a high baseline drift towards the end of our analysis time, a lot of unwanted peaks, very uneven baseline. So this is making our chromatogram harder to read, harder to analyze. So the last consumable within our injection port is the O-ring, and it is a very small thing, but the failure in working condition of the O-ring can lead even to GC shutdown. It might be crazy to think that that very small bit can cause a lot of problems and even stop our run. So here we've got a diagram of the injection port, once again reminding us where the O-ring sits. And when the O-ring, so O-ring can be called also liner seal. The both terms are interchangeable. They mean the same consumable, the same thing. So if it's faulty, our GC cannot maintain the pressure in our injection port liner, and it will shut down. So the easiest way to observe this, our GC will be beeping that, hey, there is loss of the pressure, and on our chromatogram, we will see just the first part of the chromatogram, and the second part of the chromatogram will be lost. So, but the previous situation was where the O-ring was completely faulty, so GC was losing the pressure. But sometimes our O-ring can be just slightly damaged, resulting in just a small drift in our flow. So the GC will be still maintaining the pressure, but our gas flow could be affected. And here we've got example how this drift, how this can affect our analysis, our peak shapes. So at the top, we've got flow of the gas at 31 centimeters per second, and we can easily see three peaks. Essential oil analysis was done in this case. So the first peak was for camphor, second lionol, and third lionel acetate. So we can see the clearly three peaks baseline resolved. But when our flow was dropping a little bit to 27 centimeters per second, we can see that the first two peaks have started merging. So we are not able anymore to quantify them accurately. And when our flow was dropping even further, the first and second peaks merged completely. So as you can see, a lot of issues which we usually would assign to the performance of the column are not actually related to columns, but to injection port consumables. And injection port consumables are small things, and they are significantly cheaper than the columns. But changing them on regular basis and keeping track of them can improve your results, as well as can extend life of your GC column. So if you change your consumables on regular basis, you don't have to change your column so often. So the last bit, how to keep the track of our GC consumables. So how do we know how often we should change them? The first thing, we should keep a logbook for each of our GCs in our laboratories. We should keep track of how many injections has been made with each of the consumable. And when something is going wrong, we should make a note what we've done to fix the issue. And using all of those information, we can develop a routine maintenance schedule to help us change the DC consumables frequently enough to avoid problems. And very often we can hear the question, okay, so how often we should change our consumables? And the answer is not easy. It will depend on your GC use, on your types of samples, on your type of analysis. So someone can be changing the liners on a weekly basis, but someone else during the different type of analysis can be changing liners on a daily basis. So this is important to keep the track of how many injections has been made. And even if you're unsure if you should change your consumables based on your chromatogram, the easiest way to develop your schedule is just to have a look at your liner, and then you will know if you need to change this or not. You will see if it's dirty. I know it will take some time to have a little break for the instrument, but in the long run, it is more beneficial. So you will know, okay, that's my point where I need to change my liner, where I need to change my septum. And the last bit, if you need any further helps troubleshooting your issues related to injection port, please connect to us through tech support at Trajan Scimet or visit our website and support pages. As I've mentioned, we've got some tips and selection guides related to DC liners there. So I hope this information would make your life a little bit easier and the choice a little bit easier for the injection ports.